This takes us to the last presentation of the workshop, Professor Sir Anthony K. Cheetham. He doesn't need an introduction, but I'll just say a few things. He's a research professor at the University of California, Santa Barbara. He's not only a leading solid-state chemist, but also has impacted science and technology community in various parts of the world. In January 2020, he was knighted by the King for services to materials chemistry, UK science, and global outreach. Over to you, Tony.
Thank you very much, Umesh, and thank you all for being here right at the end of the meeting. And this is one of the reasons that we have the banquet at the Palace on the last evening, because it encourages people to stay until the end. So I'm going to talk again about MOFs, and you'll see that my MOFs are basically the world's simplest MOFs, and I'm a very old man now and I can't afford these expensive ligands, so we're working with the cheapest metal, which is aluminum, combined with the cheapest ligand, which is formic acid. And this, by the way, is the University of California in Santa Barbara. It's a rather beautiful location. And just the outline of what I'll say, I'm going to talk a bit about perovskites. We've obviously heard quite a lot about perovskites during the course of the meeting, and say just a few words about our work over the years on halide and formate perovskites, and then focus on the ReO3 type perovskites, which are pertinent to the work on aluminum formates and the related formate materials. So I'll talk about CO2 capture, air separation, hydrogen storage, and also adsorption of inert gases. And then I'll finish off with some future challenges and opportunities. So everybody, I think, probably knows the perovskite structure now, if you've been coming to the talks, the ABX3 perovskite structure, which in the world of oxides is the kind of workhorse of condensed matter physics and solid-state chemistry. And we've just celebrated the 100th anniversary of the determination of the structure of the first perovskite in 1925. You can make perovskites not only with purely inorganic systems, but you can replace the A cations, such as the calcium in calcium titanate, with simple organic cations like methyl ammonium here. And that has given rise, as many of you will have seen during the meeting, to the lead halide perovskites, which have had a massive impact in the development of photovoltaics over the last 15 or 16 years. You can also replace the oxygen in the perovskite. If you look at the oxygen bridge between the B cations, you can replace those with organic bridges, and in particular, the organic bridges based upon formate, the simple formate linker, bridging from one cation to the next, have been extremely important. And these, like everything else, these have been known quite a long time, but were really highlighted by some work by Gao Song in 2004 in Beijing. And we worked on those when I was first in Santa Barbara, and then when I moved to Cambridge in 2007, we worked on those materials, and there's always something new to find, as we've seen throughout this meeting. And what we discovered was that these formate perovskites, like the dimethylammonium manganese formate, you see the copper one up here, they order ferroelectrically. So they're excellent ferroelectrics at low temperatures. And we observe the ferroelectric phase transition. And because you can replace, say, the magnesium or the zinc in this case by transition metals, you can actually make them both electrically ordered as ferroelectrics and magnetically ordered. And so we showed that they will make multiferroic materials and with transitions at somewhat disparate temperatures. This is the ferroelectric transition, this is the magnetic transition. But they actually show nice magneto-electric effects. And I show you this because we've been working on these materials for a long time. And the last stuff that we did in the last sort of 5 years or so was to look in detail at the phase transitions in some of these materials, both computationally and experimentally. And so that takes me to the next phase of the work I've been doing in the formates, because there's a related material, excuse me, back. There's a related structure here. If you take the A cation out of the perovskite, you have what's known as the ReO3 structure. And it simply is a structure with no A cation in the cavity. And you can do this with formates, it turns out. You can do it with lots of other things. And Ramsa Shadri and I and a couple of our young co-workers wrote a review on this a couple of years ago, and all the different materials. And that drew my attention to something I should have noticed a long time ago, which was aluminum formates. So instead of having a cation in the cavity and a divalent metal, like zinc, you can have nothing in the cavity and a trivalent metal, and so you can make aluminum formate, just simple aluminum formate here, which I call the world's simplest MOF, starting with aluminum hydroxide and formic acid. So it's essentially a perovskite with nothing in the cavity. Except, if you look carefully at the crystal structures, it does have something in the cavity, and what it has in the cavity is carbon dioxide. And the first of these materials to be characterized was in 1999 by Daniel Gatteschi and his co-workers in Italy, and they made this manganese analog of the aluminum formate. So they did it with manganese 3+, and they published it in Angevanta and said, it's interesting, it's got CO2 in the cavity, and nobody took much notice of it. But then about, 8 years later, a Chinese group wrote a very nice paper in Inorganic Chemistry, and they looked at the aluminum analog, the gallium analog, the iron analog, and the indium analog, and they published crystal structures for all of them, and they've all got CO2 in the cavity, just like you see over here. Here's the CO2 in this kind of ReO3 cavity, neutral CO2. So this was kind of hiding in the open, as it were. Nobody really thought very much about it. And when we're doing the review, this struck me that if it's so specific for CO2 in the cavity, can we do two things? Can we get the CO2 out without collapsing the structure? And if we do that, can we get the CO2 back in? Does it become a good sorbent for CO2? And so the Chinese group had tried to do that, so they did see the potential of it, and they tried to do it with the iron compound. It turns out that the iron compound, you can't activate it and remove the CO2 because the iron 3+ oxidizes the framework when you do it, so it just collapses. So we looked at this activation process with aluminum. Being an old zeolite chemist, I knew that aluminum was a much better bet than iron because it won't have any redox properties. And so we showed that you can activate the aluminum formate and remove the CO2 from the cavity. And you end up with a porous MOF then. And this porous MOF is stable up to about 250 degrees C. This is just the activated material. And the composition that I'm showing here is the composition that was reported by the Chinese group. We've just been doing some NMR work, which I don't have time to discuss, but in most of the samples we make actually don't have CO2 in the cavity, it turns out. They've got formic acid in the cavity, and they've also got some carbonic acid in the cavity. And you can see this in the NMR. Notwithstanding that, having activated it and done the crystal structure of it very, very carefully, it shows some negative thermal expansion or zero thermal expansion at low temperatures. We are able to show that it will reabsorb CO2. And it gives you very respectable loadings of about 4 millimoles per gram here. And so this is the activated material. And of course, if you take a material that's not been activated, still got stuff in the cavities, doesn't absorb anything at all. And we have this here because we wanted to file a patent and demonstrate that this was genuinely new. And so the heat of adsorption is between 47 and 48 kilojoules per mole. So Andy Cooper was talking about material the other day, which was about 40, and he said that's very high. This is extremely high for CO2 in a MOF-type material or porous material. And that's because the CO2 is hydrogen bonded at each end within the cavity to the hydrogens of the formate linkers. So you get hydrogen bonding between the oxygen, the CO2, and the formate linkers. So we did some very nice neutron diffraction work on this, which was actually done by Hayden Evans at NIST, and sort of beautiful Rietveld refinements. And I've worked on the Rietveld method for about 50 years. This is, as good as it gets. And so what we did was to do the neutron diffraction as a function of loading the CO2 into the system. And so you can see the CO2 going in because it appears in the structures. And there are two types of cavity here, not just one, actually. And you can see the CO2 going into both of the cavities as you load it up. So these are the CO2 loadings as you increase the pressure. So it goes very favorably, actually, into both types of cavities. So we thought, could this potentially be used for capturing CO2 from flue gases? There's been a huge amount of interest in this for several years. We had a lovely talk yesterday about doing this with, or maybe it was this morning, doing it with amines and how the issues around doing it with amines because of the energy required to remove the CO2 from the amine solutions afterwards. So essentially for flue gases, what you have to be able to do is to separate CO2 from nitrogen, and flue gases contain a lot of hydrogen. But the very important thing to remember, if you think you're going to solve this problem, you've just got to remember that there are 2,500 coal-fired power stations around the world, and each of them will burn about 36,000 tons, 10,000 tons of coal every day. So you're generating 36,000 tons of CO2 per day in each of the 2,500 plants. So it's a massive amount of stuff. And that's one of the reasons that I like ALF, because if you're going to address a problem like the CO2 problem, then you have to be scalable and simple. Otherwise, the quantities of material that you need are out of sight. But the challenge here is that the flue gases contain a certain amount of water, or steam, of course, since it's in the vapor phase. And most MOF-type materials are unstable in steam above room temperature. And ours is no different, as I'll come to, but the surprising thing that we found was that ALF will not, and we call this material ALF, will not absorb nitrogen at any temperature, which is kind of bizarre because nitrogen is awfully small. People use it to determine the pore size of their systems, and nitrogen just won't go in, even though CO2 goes in extremely effectively. So if you look over here, the blue line is the CO2 adsorption as a function of pressure. The orange line here is the nitrogen adsorption, which is negligible. And so we have a selectivity of CO2 over nitrogen of 400 or so. This is the IAST selectivity that you do from the single gas isotherms. But it's incredibly selective for CO2. And so it does have the potential to capture CO2 from flue gases. However, like most other MOFs, ALF is not stable in moist atmospheres if you take it significantly above room temperature. Say, take it to 50 degrees C, and it starts to fall apart. And we understand the chemistry of that quite well, but it's a serious problem. In principle, nitrogen should go in. It fits in the cavity, and in fact, the heat of adsorption of nitrogen is nearly 30 kilojoules per mole. Water should go in. It doesn't go in very easily. We've done water adsorption isotherms. Room temperature, it doesn't go in easily. But you see in the two different types of cavities, the calculated heats of adsorption of CO2, and with the 48 in the small cavity and 36 in the smaller cavity, in the larger cavity. There are only sort of 25% of the cavities are large, so most of them go into the CO2 goes into the smaller cavity with its better heat of adsorption. So clearly there's a kinetic thing here. CO2 will fit in the cavity, no problem. In fact, formic acid will fit in the cavity, but nitrogen won't go in. And I'll come back to the reason for that later. So just at this point, what are the pros and cons of the ALF? Aluminum formate just requires formic acid and aluminum hydroxide. And they're roughly $1 a kilo each. But of course, if you have a kilo of aluminum hydroxide and 3 kilos of formic acid, you basically get 4 kilos of ALF. And so we reckon, when I made this slide, we thought we could make it for a materials cost of about $2 a kilo. And we now know that we can do it significantly cheaper than that. If you compare it with most other MOFs, that we're sort of roughly, it's a minimum 10 times cheaper, and in many cases, maybe as much as 1,000 times cheaper. And you can make kilograms of this in the lab. A farmer with a bucket in Rasselhamer could actually make this in a field. It's so easy to make, especially if you get the solar energy heating it up a little bit. So it's very easy to make. And one other thing I'll say about it, it has excellent mechanical properties, but it's sensitive to moisture above about 30 degrees C, and it hydrolyzes to a chain structure which has no porosity. So you obviously don't want that to happen. So one of the things that Rajesh Das did, who's a postdoc who worked with me in Singapore, he's just about to finish in Singapore, was to explore the possibility of making it hydrophobic. And we explored a variety of polymers, fluoropolymers, and the one that worked really well is PVDF, polyvinyl difluoride, and all you have to do is put the PVDF into the reaction mixture with the formic acid and the aluminum hydroxide. You don't need any other solvent because formic acid's a liquid, so it acts as a solvent as well as the reactant. And by mechanism that we don't understand, when you do that, the material still crystallizes out with the PVDF on the surface. And so these are the crystals that you get in the absence of the PVDF, and this is what they look like in the presence of the PVDF. But you can see the contact angle goes from about 39 degrees for the regular ALF to 112 for the PVDF-coated material. So it's highly hydrophobic. And I won't go through all the details of the characterization. It's still stable to 250 degrees C. What this slide tells you is that it has the same performance and slightly better performance even than the regular ALF material without the PVDF. And we need about 7% of PVDF, so it doesn't dramatically alter the costing in terms of the materials. And so we did, for example, cycling of the materials, sort of repeated CO2 adsorption, desorption, and followed by heating it in a moist gas atmosphere and then repeating it. And we did that for about 10 days, and there was no diminution of performance. Having said all that, the flue gas is so difficult. You know, saying you can do it for 10 days is one thing. Doing it for 6 months or a year, which the companies who've got these plants will want to do, is a different matter. And I'm not confident that any of the MOFs are going to survive under those sort of extreme conditions, even ALF with the coating. But you can make it hydrophobic. One other thing that's worth pointing out, if we make solid solutions of aluminum with iron, then you can get enhanced performance. The pure iron compound you can't activate. If you go to something like 50-50 or up to about 70% of iron, then you get better kinetics than we get with the pure aluminum compound, and we preserve the performance. And of course, iron hydroxide is also very cheap. So we can certainly separate CO2 from nitrogen, and so we are interested in whether we could potentially do it with biogas and from fermentation processes. You know, lots of cities have fermentation plants where they sort of digest agricultural waste or food waste and so on and produce biogas. And biogas is mainly methane, but it's got a lot of CO2 in it, and then a sort of small amount of nitrogen and a very small amount of hydrogen sulfide. And so we thought, well, can we separate, say, CO2 from the biogas so that the biogas is purer, primarily methane? And that works extremely well. And so what we discovered, and there's lots of data on here, what we basically discovered is that ALF will absorb CO2, but it won't absorb any hydrocarbon. Not only will it not absorb methane or ethane or ethylene, it won't even absorb acetylene. And so this kind of worried me because I thought we don't understand this very well, because acetylene is kind of thinner than CO2. So if this was all about size and, say, nitrogen being a bit bigger than CO2, so nitrogen won't go in. Methane's okay, because methane's very large. We don't expect that to go in. But why won't acetylene go in, which is smaller? But the separation factors for, this is CO2 here. These are methane, propane, ethane, acetylene. There's virtually no adsorption of hydrocarbons. So we get the selectivity for the CO2 acetylene separation is nearly 10 to the 6. It's absolutely massive, which is staggering when you think they're more or less the same size. And then in the case of the methane from CO2, the separation factors, so they're nearly 10 to the 4, nearly 10,000. So it's massively selective for CO2 over any hydrocarbon at all. And so this puts ALF in a different league than everything else for these applications when you compare it with other molecular, and well, primarily with other MOF-type materials. So initially, and when I made this slide, I really believed it. I thought it was size selective because we could separate CO2 from nitrogen, and nitrogen is bigger than CO2. And I thought, we should be able to absorb oxygen and maybe separate oxygen from the nitrogen in the air. And so that seemed a good thing. And so we've been looking at that. And so if you get medical oxygen, it can be made one of two ways. It can be made with cryogenic distillation of liquefied air. That obviously, takes a lot of engineering and expense. Or if you see these portable oxygen generators that people, say with breathing problems and so on, carry around with them, those use typically lithium zeolites, something like lithium zeolite X. And what happens with the lithium zeolites is that the zeolites preferentially absorb the nitrogen. And this works because the quadrupole moment of nitrogen is about 4 times higher than that of oxygen. So you get an interaction between the lithium and the nitrogen. So let's see what happens with the O2. So good news is that ALF will absorb O2. This is data for the iron-doped system. This is the nitrogen again here. So we have a selectivity of about 100 for oxygen over nitrogen. So just notice, this is the other way around. It's not like the zeolite. We're absorbing the oxygen that we want instead of absorbing the nitrogen that we don't want, which is 80% of the air. So this has a massive advantage over the zeolites. We're absorbing the stuff that we need. And the downside, when we initially did this and published it, is that we need to cool it down to about 200 degrees Kelvin to dry ice temperatures in order to make it work. And because the heat of absorption of oxygen is not as good as the heat of absorption of CO2, which we can easily do even above room temperature. So that's not ideal, but under those conditions, there's no nitrogen being adsorbed at all. This is the nitrogen adsorption isotherm. And so initially I was satisfied with that. I thought, well, we could actually potentially commercialize this, and all we need is dry ice, and we can do it easily at 200 Kelvin. And then I went to India and discussed it with Pratap and the Professor Diwakar in chemical engineering at the JNC. And he was interested to do this because they have a small startup doing this kind of thing. But he said, we don't want to be cooling it. We don't want to be going to villages in India where they need oxygen and cooling it. So can't you do it at room temperature? So we since then have done that. We've not published it yet, but we just filed the patent a couple of weeks ago. And so we're ready to publish it. So what we're doing with this is a pressure swing adsorption. With the CO2, we do a temperature swing because it will adsorb at, say, 25 degrees centigrade and desorb at 70. So it doesn't need a lot of energy to get CO2 out. Here, what we're doing is taking the pressure up because even though it won't adsorb so much oxygen at room temperature as it does here at 200 K, if we do a pressure swing adsorption and cycle between, say, 10 atmospheres and 0 atmospheres, then it will adsorb splendidly at room temperature with the same selectivity that we see in this case. So our selectivity, as I say, is about 100. The zeolites absorbing the nitrogen have a selectivity of between 5 and 10. So this is kind of game-changing potentially. And I think this is the easiest thing for us to look at commercializing. So we've been talking to a couple of companies, both in the USA and elsewhere. So these are just the heats of adsorption. You can see oxygen, the heat of adsorption is actually less than that of nitrogen, even though the nitrogen actually won't go in. This we'll publish a paper soon on the high pressure separation, high pressure up to 10 atmospheres, which is kind of standard conditions. And I think we can use this without a great deal of further research other than pelletizing the material. Once you have something that really works, then you realize that people want many kilograms of it, and they also want it in pellets rather than a fine powder. So we've been working on making pellets or extrudates to actually do that. So, of course, the other very small molecule that people are interested in is hydrogen, and there's huge amounts of work been going on over the last 20 years or so on hydrogen fuel cells for cars. BMW will sell you a fuel cell powered car, and obviously the range depends upon how much hydrogen you can store. And so the metric that people use, they compare, say, using a molecular sieve like a MOF with storing the hydrogen simply under pressure. And they store it at 350 atmospheres. And if you're driving a car with a large tank containing hydrogen under 350 atmospheres, you basically are sitting on a bomb. And so from the safety perspective, having the very high pressure hydrogen is not ideal. Has a lot of other attractions. It only emits water instead of CO2 from gasoline, for example. And so we've looked at this, and the adsorption of hydrogen is really good. All the molecular sieves have to be cooled to adsorb hydrogen. So whatever MOF you use, or COF, or zeolite, or anything, it will have to be cooled. And so this is the performance of our material. Optimally, it works at about 120 K. And as you increase the temperature, you can see to 160, 200, 233, and so on. It goes down. That's a sort of normal thermodynamics. But under these conditions, and at quite low pressures, this is not 350 atmospheres of hydrogen. This is, say, 15 to 20 here. And the heat of adsorption is nearly 9 kilojoules per mole. Our hydrogen uptake is about 11 grams. The kind of best in class, if you look at, say, Professor Jeff Long's MOFs and the sort of nickel-based MOFs that he's developed, they'll adsorb about 18 grams of hydrogen per kilo of sorbent. The DOE set a target for this area, and their target was they wanted to be able to store 18 grams of hydrogen at a cost of $10 per kilo of sorbate. So that's 1.8 grams hydrogen per dollar. We don't have to be the best performing material to be the best choice, because we can store 5.5 grams of hydrogen per dollar of material here. And so we're about 3 times better than the DOE target. The only problem is, because we store only about 60 or 70% of what the best MOFs will do, our range in the car's not going to be great. If you went and thought you'd go to Dubai and back for the day, or even worse, Abu Dhabi, you'd run out of gas before you get home again. So this is not the ideal solution because range is so important, but it's a very attractive solution for stationary fuel cells. And so we are looking at things like backup power systems for data centers, for example. And so we've done a techno-economic analysis of this, and we have this niche of being at low pressures and only, sort of intermediate temperatures compared with the high pressure, low temperature conventional MOFs, and then the very sophisticated MOFs, which are high pressure but higher temperatures. So this is something that my colleagues at NIST are working on at the moment. So there's something about the hydrogen here. Let me just show you something else. I showed how the amount of hydrogen reduces if you go to to higher temperatures, 120, 200 it goes down, and 230 and so on. I showed you that before. The funny thing is here, if you take the temperature down, you'd expect to get more and more gas going in if you went below 200. But what happens, if you're at 120, you're up here. Then if you're at 90K, you're here. And then if you're at 77K, you're way down here. So as you go up in temperature, the amount of gas adsorbed goes down. And as you go down in temperature, it goes down as well. And so this is a characteristic of what's known as an ultra-microporous material. And you see it here for hydrogen. So I'll quickly show you what happens with the inert gases. They show exactly the same effect, and these are some of the adsorption isotherms here. If you take helium, you have to cool it down to about 70 degrees Kelvin, and then it will adsorb. If you go down to 50 degrees Kelvin, it won't adsorb. So there's a very characteristic temperature for helium adsorption. Same for neon, and the same for argon. In the case of argon, it's sort of above room temperature. So these materials, these ultra-microporous materials, of which ALF is a classical example, have critical gating temperatures, which makes them really interesting for doing adsorption properties. And so we've been looking at the reason for that with my colleagues at NIST and Hayden Evans in particular. So those things I showed you were the temperature programmed desorption. So we push the inert gas in and cool it under high pressure, cool it down, and then we follow what happens as we heat it up. That's how you get those things. And we have that data for not only for inert gases, we have it for acetylene. See, acetylene, we kind of never get to the gating temperature. There's some hypothetical gating temperature at very high temperatures, but at that temperature, the thermodynamic adsorption has disappeared, so nothing goes in. And this is the gating temperature for hydrogen here, for oxygen, close to room temperature. Nitrogen, again, is very high. That's why nitrogen won't go in. And CO2 is very high as well, but it has a very good heat of adsorption. So the reason for this is that the ALF is very dynamical. It's not kind of rigid framework like I've shown you. It's quite dynamic framework. And as you warm it up, the windows into the cavity where the hydrogens are from the formates, they just sort of expand. The windows get bigger, and so you get to the point where larger and larger molecules will go through. Or molecules that are interacting with the formates in the ring. So in the case of we've done lots of vibrational spectroscopy, Raman, inelastic neutron scattering, and this, for example, is the dynamics, the blue lines are dynamics of the sort of wagging of the hydrogens. And we've done molecular dynamic simulations on this. So the system opens up with temperature, And as you go further up in temperature, other things will be absorbed. And we can calculate the activation energies. CO2 is a special case because it interacts very favorably with those hydrogens, and that kind of smooths the path into the cavity. So one last thing, we've made a very stable form of aluminum formate, of manganese formate, unlike the one that Gateski made 27 years ago. Ours is stable at room temperature, you can activate it and so on. His had to be kept in a refrigerator and was incredibly sensitive to moisture and air. And I think because of the way he made it. So we developed a nice way of doing that. And this is all the technology. We've got one issued US patent as of November and 7 publications and counting in this area. And this is scalable, earth abundant, low cost. It's got amazing properties. If you thought, if you wanted to absorb anything very effectively, then you know CO2, oxygen and hydrogen are kind of perfect systems. And it has this, we can make it hydrophobic. It's got this ultramicro porosity. And I just mentioned Hayden again. Whoops. Dinesh Mulangi, who did the original synthesis and activation work and so on. Rajesh Das, who's been working with me more recently. And we work very closely with the computational colleagues, Jerry Deng and Piero Canepa, Hannah Broinig at Lawrence Berkeley doing the techno-economic analysis, and then colleagues at NUS, Dan Zhao in particular, who's been doing a lot of the adsorption and breakthrough data that we have, and people at NIST with Craig Brown, Tanner Yildirim. And we've done this because I'm such a poor man, we've done it, my original grant to do this was $150,000 over 2 years. So it's been done very cheaply, and I'd be happy to answer some questions. Thank you.